Okay, so we have these two beautiful questions. One is about a spinner. The spinner can either come up 0, 1, or 2. The other one is about coin flips. The number of heads can be either 0, 1, or 2. So these seem like very similar situations. What did you guys say? Let us reveal what people said. So for the spinner, 78 to 1, people said true. True is the right answer. It is probability 1/3 to come up 2 on the spinner. 1/3, 1/3, 1/3. You can see from the pie graph, they take up 1/3 of the circle. It's all very intuitive, and it's exactly what you think. Great job. What about the heads? What about the heads? On the heads, 71 people picked false, and only 8 people picked true. And once again, you guys got it right. So very well done. Everyone figured this out. What is the point of this question is to show you that just because you have the outcome 0, 1, 2, you might have 2 different probabilities. So let's draw a little cartoon of what is happening here in our brains. This is like the cartoon for how probability works. Let's go to a blank page. So here is us. This is us. I'm a stick figure, and I'm thinking in my head about the spinner. So if I'm thinking of the spinner, I can see it has equally likely outcomes. I can color it in even. Here's yellow, here's orange, and green, and I see the 3 equally likely outcomes. So I can see that the 3 parts of the spinner are all kind of interchangeable. In fact, you can imagine, if you like to think of symmetry, you can imagine all the 3 segments are symmetric with each other. The orange segment and the yellow segment, you can imagine a different universe where someone had cut them out and reversed them, and how the spins come out wouldn't change between our universe and their universe. So because these 3 things are kind of interchangeable, this is why we come up with the state space, which is either 0, 1, or 2, and importantly, with the probability rule, which is the equally likely rule. Let's say equally likely rule. Let me not write equals to confuse people. It is the equally likely rule. Okay, so doing the spinner, we look at it, we use our brains, we see they're equally likely. That's why we came up with the state space with 3 things, and that's why we use the equally likely probability rule. For the coin flips, it is different. So for the coin flips, I'm thinking of the coin flips over here. And I have 2 coin flips. So one of them, I don't know, it's like flipping through the air like this. Here's the other one flipping through the air like that. Those are supposed to be coin flips, okay? And now, when you look at coin flips, what is the symmetry in a coin flip? In a spinner, it's very obvious that there's the 3 segments of the spinner. Those are the 3 symmetrical things. What are the symmetrical things in a coin flip? Well, it's the sides of the coin. The heads and tails on the left coin, you can flip it upside down, right? In a different universe, you can imagine at the Canada Mint where the coin was pressed, if they had turned it upside down, then the head and the tail would be reversed, and everything would be the same. So by that symmetry of reversing the heads to the tails and reversing the heads to the tail in the other one, we know in this situation that the number of heads, 0, 1, or 2, is not the thing that is equally likely. So the chances of getting 2 heads has nothing to do with this space 0, 1, 2, right? It's a completely different probability space. And in fact, it's kind of a baby version of the one with the dice that we've been doing the whole time. What is the state space in this case? It's either heads, 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 tails, tails, heads, or tails, tails. Right? That's the probability space. And now I can use the equally likely rule, but it's a different space. Okay, so space, when I say space, I mean sample space or probability space. That is the key thing to keep your eye on. And again, by symmetry, we know these are equally likely. By the heads to tails symmetry, we know equally likely. So at the beginning of the course, we're always using state spaces where we're using the equally likely probability rule. If you want to know the probability of something, you count the number of the number of outcomes inside the event you're looking at. You count the total number of outcomes and you divide them. So for example, the probability of getting 2 heads, the probability of 2 heads is 1/4. Because there's one outcome where you get heads, heads, and there's 4 outcomes total, it's a quarter, not a third. All right. You guys all got that right? It was very good. Why am I bringing this up? The thing that I want you to focus on is that the state space matters. Question?
If you're giving us this question like on a quiz Thursday, would you want us to show us writing out all the possible outcomes, or could we just do 1/2 multiplied by 1/2?
Okay, yes. So another way to do it, I see. You're like, I want to do the problem a different way. I want to do the probability of 2 heads, and then you want to say the probability that the first one is heads, and then you're saying times the probability that the second one is heads. And then you're saying this is a half times a half, which is equal to a quarter. This is like your proposed solution. Is that right? So we will get to this when we do a topic called independence, the justification of why you can write one event as the product of 2 events uses something called independence. So if this was on a quiz and we had already done independence and you wrote this, you would not get full marks. But if you also wrote by independence, then you would be on your way to getting all the marks. And we will get there when we do independence in the next week or so. Great question. So for now, I want you to think of the state spaces. And the reason is the state space is really important. We're going to do conditional probability, and you're going to see how the state space really enters in. It is, in a lot of situations, you can sort of avoid thinking about the state space and only operate in terms of numbers. But what we're trying to do is to get you to think about it in situations where it's good to think about it. Of course, you want to be able to do both, but like this is the core of what probability theory actually is. And you'll see when we do independence, it really is all about the state space again as well. Okay, great question though. Anyone else? Okay, now let's go back. So I did this warm-up question to get you guys thinking about the state space. Now, let's go to the thing where the class was split at the end of class last time. So 49 people voted for the probability changes, and 40 people said the probability doesn't change. And that was last class, where we dealt out a card. So I had these 10 cards, ace through 10, and I dealt one out. So this was dealing out a card. So this was from last class, deal out one card from ace 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? And the event we care about, the student wins the prize on the event. I'm going to call the event W. It's the event of A. So if an A comes up, then you get a prize. Otherwise, you get no prize. All right. And originally, we were thinking like this. We were sitting here over here in our little stick figure, and we're saying the deck is well shuffled, and therefore all the cards should be equally likely. So originally, and let me actually draw a big originally. This is before anything sneaky happens. Originally, it looks like this. We see the deck is shuffled, and therefore we come up with the state space, which is exactly the set of cards. 1, ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we know it's the equally likely probability rule. Equally likely rule. So when I first give the card to the student, today Gary's sitting here. Let's give Gary the card. Okay, here you go. Right? So we're hoping for an ace, but we know the possible things are ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we know they're equally likely because we see the deck is shuffled. We can think of the symmetry of swapping one card with another card, and that doesn't change the situation. And that is why originally the probability is 1 over 10, right? So originally the probability is equal to 1 over 10. Let me say the probability of winning, the event W, is 1 over 10. There's one card over here, and there's only one outcome that we win on. There's 10 outcomes total. They're equally likely, so the probability is 1 over 10. That's the original situation. But now we're going to have this funny, sneaky situation where before we reveal the card, I say, by the way, would you like to know that this card is a 4? Right? And now we have some new information. Okay? And let's put a cartoon of what the new information is like. And so this is the new situation down here. This is the new information situation. Okay. And so now I can see I know something new, right? I have something new in my brain, which is that the 4 was revealed, was not the card. I know the card is not a 4. 4 was not the card. Right? So because I see a 4 over here, I know the card in front over there is not the 4. And this is going to affect how I think about things. There are a few different ways you could do this. One is you could just completely ignore the old situation. You say, forget about the old situation. Now we're in this new situation. Things are different. But in practice, what we do is we've come up with a system of notation where we take the old situation and we write the new situation as we have the old situation plus the new information. So we're kind of thinking of updating the old situation with the things that are new. And in this situation, the event that 4 was not the card, that's an event. 4 was not the card is an event. That's the event. I'm going to call that E for event. Oh, actually, why don't I call it I for information? Let's call it I for information. So the I for information event is the event ace 2, 3, skip 5. Maybe I'll write 4 and I'll cross it out so you make sure you know it's not there. No 4. Not there. So the 4 is skipped. Ace 2, 3, 5, 6, 7, 8, 9, 10. This is why we taught you things like complement. Instead of writing out every single thing, you could write not the event it is a 4, not of 4, or you could write 4 complement, right? So this little complement means everything except for it's a 4. There's definitely not a 4 there, so that's the event we're on. That is the information we have. And again, you could now write something like the new probability. So you could say like probability new of W is now 1 over 9. Where new probability means I'm thinking now of these 9 elements as my new state space. Out of all the possibilities, there's 9 equally likely outcomes now. And I can say the new probability with my new information of the same event as before, that it's an ace, that is 1 over 9. This gets very confusing very quickly. So in practice, we don't write P new. We have a special notation for it. And I'm going to show you that now. What we do write is we write the probability of W, and then we do this line I. And we say that this is 1 over 9. Okay? And this line, you read it out loud as given. So given is how you pronounce this line. And so you would read this out loud as the probability of W given I is 1 over 9, or the probability of winning the game given the information we have is 1 over 9. That's the right kind of thing. And why is it 1 over 9? Like, how did we come up with the formula 1 over 9? Let's go a little bit more in depth of how we came up with 1 over 9. Well, it was the number of ways we win divided by the total number of things that can happen. So ways we win in new information divided by the total number of things that can happen. Total number of ways. Total number in new information. So it's important that we sort of include the new information. Note that the new information is appearing both in the top of the fraction and in the bottom of the fraction, right? If you have some new information, it can affect the ways you can win. In this particular case, it didn't affect it, right? The ways we can win is still just the ace. The ace is the only one where we can win. So the top is 1. There's one way we can win, right? So it's let's say the number of the things in ace. And on the bottom, it's the number of things that are in the information. It's the number of things in I. Okay. Yeah. So there's one thing. It's the number of things here in I, which was 9 things, which is how I got 1 over 9. Okay. So here is the formal way you can get 1 out of 9. I think 1 out of 9 is quite intuitive, but it's good to see like how we're getting there formally with all the sets and things. Any questions about how I got 1 out of 9? Yeah.
I don't know if this is a dumb question, but when he pulled up the card originally,
Yeah.
he had a 1 out of 10 probability.
That's right.
But when you removed the card, he still had a 1 out of 10 when he did initially pull it out. So you pulling up the card doesn't really change his probability.
Yes. Okay. This is an absolutely fantastic question. Like, if we were in physics class and I said, I get out a ruler and I measure this piece of wood, how long is the piece of wood? And I say it's 1/10 of a centimeter long. And then I come over here and I do some stuff with cards over here. And then I come back and I'm like, now the piece of wood is 1 out of 9 centimeters long. You guys would all think I'm insane, right? Like, how is it that doing something with these cards can change something on that side of the room, right? And the answer is, the probability is not on that side of the room. Where is the probability? It's in my brain. Look, right over here, right? Probability is something, just like our warm-up question. Why was it that the chance of a 2 coming up here was a third and the chance of a 2 coming up here was a quarter? It's what is in our brain, and that what is in our brain filters into what is the state space and what is the probability rule, okay? And depending on the information you have and what is in your brain, you will see it differently. Actually, here, this is a fun little experiment. Let's, I'm gonna go to this gentleman right here. We're gonna look at all the cards, okay? So for us, the probability that Gary has the ace is very different than the rest of you guys. Right? We have different information than you guys do. We know for a fact if Gary won or not. I can look at all the cards. I can see, does Gary have the ace or not? So for me, it's either a 0% chance or a 100% chance. For all of you, because you don't have my information, ha ha ha, it's still a 1 out of 9. Okay? So probability really depends on what you know. And this class is really like, how do you take what you know and turn it into like math that you can do? Right? But it is important to remember it does depend on what you know. Gary, would you like to reveal your card? He's got it. We did it. Okay, I owe Gary a copy. So for me, when I revealed all the cards, I knew there was a 100% chance that he had it because the ace was not in the cards I looked at. So even without looking at his card, I knew what would happen for sure. Right? You can imagine if I only looked at half of them, I'd have a pretty good idea, but not 100% sure. And depending on what happens, this idea can filter into your probabilities. And this is why this conditional expectation thing, this conditional probability, this given, is so important. This is the mechanism by which we import our information into the math. This is the given. All right, I don't remember the original question, but it was good. A good discussion nonetheless. Any other questions? Okay, so that is the probability of winning given the information. Here we kind of did it by scratch. I do want to show you one other formula. In a lot of courses, they'll just tell you the formula and say, that's it. Here we came up with what it really means, and now we're going to derive the formula. Here is the formula. It's the old probability of winning intersection I divided by the probability of I. So this formula, I'm claiming, would give me the exact same result as 1 over 9. And again, this P here means the old probabilities, the probabilities from this picture. In the original situation, and we figured out a way to write the new probabilities. Again, let me write it one more time because it's so important. Of W given I, the new probability, given the new information we have, is written in terms of the old probabilities by doing these things. What is the relationship between what I wrote here and what I wrote down there? The total number of ways in the new information, that is proportional to I. Let me write out what these are, and you'll see exactly why they cancel out. So let me move this 1 over 9 over here. The probability of I is equal to the number of things in I divided by the number of things in the probability space S. Right? I'm taking just the bottom of this fraction and writing it down one more time over there. And similarly, in the top, what is the probability of W intersect I? Well, that's the number of things in W intersect I divided also by the number of things in S. So in this fraction, there's dividing by the number of s's in the top and the bottom, and so it cancels out. And when it cancels out, you get back our original formula, which says it's the number of ways it could happen in the new information. That's W happening and information I happening. You need both of those things. And the bottom of the fraction is the number of things in I. So these are the same thing. And very commonly, you'll see this formula with no explanation. And it really is just a convenient way to do what we were just doing. Yeah?
Sorry, what's the S?
What's the S? The S is the original probability space of the original cards. So S is all the things that can happen. The information I was everything except the 4. And yeah, now everything will work. Notice that W intersect I in this case was still the same set, just the ace, right? The information didn't change the ways that Gary could win. It was still getting the ace. Yeah?
If you were to take another card out, would
Yeah.
you add that to the variable I, or would you add a new
That's right. You would have a new event called I, like I2. So in the example I gave, you could make I2, which is now I see even another card. So now it could be like, let's pretend that I flipped over the 5. So then I2, the information on the second round, could be everything except for a 4 or 5. And then you can repeat the same thing. Now you can find the probability of W given I2, and so on. And you can, if you write W given I2, you're talking about take the original probability space and update it for information I2. You could also write this in terms of probability of W given I1, so you could find the formula that connects them as well. Very often we have sort of an original state, and then we have this like conditional state, and things don't get more complicated than that. Yeah, great question. Anyone else? Okay, so in this class today, this was the big important theory and the big important equation that had to make it on the board and in your notes. After this, we're going to do a bunch of examples that maybe get like sort of harder and harder. Of course, there are some questions on your little handout and in your homework that ask you to calculate this kind of thing. So it's good to know how to do it. We're going to do the practice problems in a second. But are there any sort of conceptual questions about anything on the board? Yeah?
What does W stand for again?
W is the event that you win the game. And in this situation, you win the game only if an ace comes up. So you might imagine a different game where you could win if an ace or a 5 comes up, right? And then if the 5 is revealed, I still have some chances to win. But in this situation, W is the winning event. The winning event. Okay. All right. Any other questions? Yeah.
If you were to pull out a ace when you were taking a card out, is that just a loss? Like
Right. So this is a great point. Let's imagine a world where the ace was revealed. That's information ace, and that's a complement. So if we're wondering if there's an ace in front of him and I pull it out of the stack, you will find, if you do the calculation, you will find that W given the information of ace is now 0. So the probability would shrink to 0. There would be a 0% chance that the ace is over there if I know for sure it's over here. And you can calculate this because the top of the fraction is going to be the probability of both W and information ace, and that will be 0. Oh, there's a name for that when two sets are like that, and there's nothing in the middle of the two sets. We have a name for that. It's disjoint. So if the information is disjoint from the thing you want, you're going to get probability 0. This is a good point. Great question. Anyone else? Okay, let's move on. We're going to move on to a harder example, and I'm going to have you guys do it first. Here's the example. Same kind of thing. Okay, so we're going to roll 2 dice. Let me actually pause responses here, so until I explain what's going on to you. And actually, I need to do something. So we're going to roll 2 dice, and just like before, we're going to say either Gary wins or loses. Okay? So we're going to say you're a winner if the sum of the 2 dice is no more than 5. So you're rooting for low numbers. Okay? Big numbers are bad. Big numbers hurt you. Before we do anything, you can figure out what is the probability of winning. This is like a question like we had from the first day of class. All right? And if you take that sheet, right, that we gave you, you can also draw it visually in that sheet. So there's a sheet that looks like this. And the probability of the event we're looking at, this is the probability space. There's some event that we're looking at. So you can draw that picture, you can figure this one out. But this is the interesting thing we're doing today. If the first dice is rolled and revealed to be insert real life result here. So we're going to roll the first dice. It's a 2. It's a 2, okay? We rolled a 2. So remember, we win or lose based on the sum of the 2 dice. Now I have revealed one of the dice. The other dice is still to be determined, okay? Now the probability of winning based on the new updated information has become blank. And I want you guys to fill in both blanks. Questions or comments before I set you free? All right, go work on the problem for a few minutes, and we'll see how many you get it right.
3-2 and it's an hour lecture, bro. I ate yeah. I mean, I guess, yeah. Yeah.
Yeah, what is the average amount of the probability? Alright, I have like 30 seconds left. Who would like more time? Who thinks that would be good? Okay, let me bump it up to by a minute or two. Okay, 30 seconds left. If you're not sure, take a guess. Okay, let's come back and see how you guys did. So far, you guys have been extremely good at these. So let's see if the streak continues. Okay. All right. So before anything happened, what is the probability of winning? This is like what we did on the very first day. That was the probability that it was exactly 3. This is it's no more than 5. Sometimes this no more than trips people up. But no more than 5 does include 5. And 76 people thought it was 10 out of 36. I also think it's 10 out of 36. I think that's the right answer. Let's do a little quick picture. So remember, the diagonals sort of contain this thing. So here's the thing. The sum of the dice is no more than 5 is this little triangular piece that looks like this. So the state space originally is everything. S equals all 36 outcomes. And let's give this thing a name. Let's no more than 5. What do we call that? S less than or equal to 5. You can call it anything you want. Let's call it A, so we don't get mixed up. A. Nice, classy math name of no thought. Okay. Sum is less than 5. And it's that little picture. Does it have 10 things in it? Because then the answer would be 10 out of 36. Yes, it does. 4 plus 3 plus 2 plus 1. 10 things. So the number of things in A, the probability of A is the number of things in A divided by the total number of things, which is 10 divided by 36. Everybody got that one right. Okay, or most people. Okay, you might have mixed up no more than 5 with exactly 5 or something if you selected 4 out of 36. Okay, but now we rolled a 2. So the first dice came up 2. What is the new probability? And this time, let's see what people chose. Ooh, a little more special. Okay, 57 people said 18 out of 36. 57 is more than half the people, but not like as decisive as before. Some people think it's 6 out of 36. Let's do it together and see what the real answer is. Okay, so what is the event that the first dice is a 2? That's another event. This is the whole point of this event notation is we can talk about these things. So let's draw this one in, say, purple. The first dice is a 2 is this nice big column over here. Right? This is the event that the first dice is a 2. What should we call that? Let's call this our information. Let me call this I for information. So I is this event. So we have this set, this event I, which is this set. We have this event A, which is this little triangle. And we want to figure out the conditional probability, right? The probability of A given the event I. Okay? And let's do it sort of 2 ways. The kind of most sane way to understand what really is going on is you delete everything that is not in I, right? So everything that's not in I, you kind of put out of your mind, and you only focus on this I. I is your new universe. Before there were 36 possible outcomes, now there's only 6 possible outcomes. And indeed, they are the 6 possible things that have happened on the dice we haven't seen yet. And inside our new universe, which only is this new yellow square, inside our new universe, there's 3 things over here where the sum is no more than 5. And there's 3 things where the sum is bigger than 5. Here are the 3 ways the sum is bigger than 5. Let me also highlight it. Let's do, what do I have left? Orange. So let's label these as well. So this one up here, this is I intersect A. This is where our information happens and we win the game. The sum is less than 5. Less than or equal to 5. Less or equal to 5. Okay. And this is our information intersect not A. This is this set over here, down here in the orange, is information. The information happened, but A complement happened. We lost the game, right? And we can reason about what the probability is going to be in terms of these numbers, but very rationally, it's 3 out of 6. There's 6 possible things. They're all equally likely, and in 3 of them we win, in 3 of them we lose. And indeed, you maybe could have just come up with this, the second dice has to be a 1 or a 2 or a 3, and that's how it works. And that's totally what's happening here. We're going to see it another way as well. But the answer is 3 out of 6. You could say by picture. You could just say 3 out of 6. Or you could say it's the number of things in I intersect A divided by the number of things in I. The information I has 6 things in it. In 3 of them we win, in 3 of them we don't win. So it's 3 out of 6. Or you could also write 3 out of 6 as the probability of I intersect A divided by the probability of the information I. The probability of the information I is 1/6. Let me squeeze that in over there. And the probability of I intersect A is 3 out of 36. So you could have gotten 3 out of 6 directly by looking at it. You could have counted the things and did 3 out of 6 that way. Or you could have used the formula and done 3 out of 36 divided by 1 out of 6. 1 out of 6 being the chances of I happening at all, and 3 out of 36 being these 3, right? From I intersect A. And either way you do it, it should simplify to the same thing, which is 3 out of 6, also known as, if you simplify this one, you'll get 18 out of 36. And that's why in the mathematize, that was an option. And let's see, how many people got it right? I think most people got it right, which is really good. Okay. So not as decisive as before. Oh, you'll notice mathematize doesn't know what the right answer was. Does anyone know why mathematize doesn't know what the right answer was? Yeah. It doesn't know what we rolled, right? I made this question, I said insert what we rolled, and the answer depends on what this dice came up. So it's a good exercise for you. You guys did the problem with what happens when a 2 comes up. If you want to think about what would happen if a 3 comes up, what would happen if a 4 comes up, think about all the different things that could come up. There's a nice relationship between the average thing and the original probability. We'll get into that later in the course, but it's a nice thought experiment. So, okay, mathematize doesn't know the right answer. The right answer is the 70% of people got it right, 18 out of 36. All right, this is a good place for questions. Questions, comments? Yeah?
Why do you go off the 2's power if we're off the 10 at the top?
Okay, this is a great...
Because, like, if you have the thing, if you do the math, it's like 3 out of 10 chance to do it.
Yes, okay, this is a fantastic, and actually, okay, this is exactly related to the next mathematized question. Why did I do 3 out of 6 instead of doing 3 out of 10? Right, 3 out of 10 is an answer to a different question. Let's write down what 3 out of 10 is. So we did A given I, and there is something else, which is the probability of I given A. And this one is 3 out of 10. This is the probability of I given A. This is asking the question, given the information we saw, that's the stuff after the line is the information. Given the information we saw, what's the probability of the event A? This thing is the reverse. This would be like, we know for sure that we won the game. What is the probability that the first dice came up 2? So where the information goes is absolutely crucial and completely changes the understanding. So this is saying, what's the probability we won the game? Let me add the words. Won the game. Won the game. Saw a 2 first. And this one is the reverse. Saw a 2 first, and then we won the game. So they're completely flipped. One is the probability we won the game given the information that we saw a 2 first, and the other one's saying, hey, I'll tell you for sure that in that class you won the game. What was the probability that a 2 came up first? And you'll notice they're different numbers. One of them is 3 out of 10, and one of them is 3 out of 6. If you're very observant, you'll also notice they're different numbers, but they both start with a 3. So these things are different, but they are related in a very nice way. There's a gentleman whose name starts with a B, who I will tell you about at some point in the future. So these are related, but different. Okay, so really good question. And if you're not able to understand the difference between this one and this one, it means you have not understood this conditional probability stuff. So you should be able to understand these 2 things. They're telling you 2 different pieces of information, and you should see why one of them is 3 out of 6 and one of them is 3 out of 10. And again, I think this kind of idea of you're deleting everything. In one universe, you delete everything except for this column. In one universe, you delete everything except for this triangle. You're going to get 2 different answers. Okay, great question. Anyone else? All right, so then the last mathematized question of the day is more practice, and it's exactly asking you to do this kind of thing. So these are the exercises that were on your dice, on your worksheet. Maybe you have some of these written on your worksheet. On the back of the worksheet, remember, was a copy of the probability space. And I want you to do 2 things. The probability of E2 given E6, and the probability of E6 given E2. Okay, so you have to remember, what is E6 and what is E2? They are these events. I think we did some examples with these ones last time. So maybe you have a head start, but try to do these probabilities. And I believe you should be able to enter your question as a fraction. So you need to get it exactly right. It's not multiple choice. Let me give you like 5 minutes to do this, and then we'll see how people did.
Because E2 can show an even number, like half the time, so the 18 out of 36. Right? plug into the formula, you get 1 in 9.
Okay, let's take this one up quickly. I'm going to leave it open while I start to do the solution. So people who are still typing in their answer, type in your answer quickly or you're not going to get the point. So we got E2, dice 2 shows an even number. We got E6, the sum is no more than 4. Let's draw these two sets. So I need another copy. Okay. So sum is no more than 4 is the same kind of triangle we had before, but this time it's like this. Right? This was E6, right? Little triangle. And E2 has a bunch of parts now. What was it? Is it dice number 2 or dice number 1? Let's make sure I get it right. Dice number 2 is an even number. Dice number 2 is an even number. So that's this row, union this row, union this row. So E2 is an event that sort of has 3 pieces, 2, 4, and 6. The other thing that will help you is to look at the intersection. So the intersection is E2 intersect E6 is over here. And once you see this, and if you remember where the given goes, then it's very quick. So if you have this picture, it's very fast. What is the probability? Let's do given E6 first. E2 given E6. And I know it takes a while to sort of remember the order here, because this looks like crazy notation. But if you remember, this is given that thing. Given that thing. So given E6, given that we're in the little triangle over there, that means we're dividing by 6. There's 6 things in this triangle. So the answer is 2 over 6. The 2 yellow things, E2 intersect E6, divided by E6. Okay? And if you do it the other way, then it's still 2 things on top, but now the numerator is all these other things. So that purple row plus that purple row plus that purple row, 3 copies of 6 is 18 things. And this is the number of things in E2. Okay. Okay, let's see if people got it right or not. I gotta open the right. Okay, most people got that one right, and just over half the people got that one right. So very good. If there's something you want to ask about, please feel free to ask on the forum or come to office hours. Do watch out for your homework due next Friday. That's going to have these kinds of questions. See you guys on Monday. Have a great weekend.
No, I would have. I didn't either.